A new paper landed quietly in the preprint archives, carrying observations that complicate what was already an uncertain picture of 3 Atlas, the third confirmed interstellar visitor to pass through our solar system. The authors report the detection of faint jets, narrow, directional structures extending from the nucleus, features that had remained invisible in earlier datasets and only emerged after careful image stacking, sophisticated filtering, and geometry-aware analysis designed specifically to isolate anisotropic outflows against the diffuse glow of a faint coma. But the shock delivered by the paper is not simply that jets exist, it's that they don't sit still. The jet directions drift across observing epochs. They split. They reappear at angles that don't remain phase-locked to any clean, repeating rotation period. And that behavior creates a scientific discomfort, because jets are supposed to be tethered to fixed vents on the nucleus. Active regions where volatiles sublimate, where dust is lifted, where the physics of heating and outgassing anchor the outflow to a specific latitude and longitude on the surface. Those vents should repeat predictably as the object spins, tracing out a stable pattern like lighthouse beams sweeping across the sky. Here, the pattern behaves like it's sliding across the nucleus, or like we're watching multiple overlapping processes that masquerade as motion. The data can be measured. The jet angles, their brightness gradients, their lengths, all can be quantified with reasonable uncertainty. But anchoring that motion to a single, coherent physical model proves elusive. The question is not whether jets exist. The images show them. The question is, what kind of object produces jets that refuse to hold still, and what that refusal reveals about the structure, rotation, or environment of an interstellar body we can barely resolve. This is the edge where photometry stops being sufficient and morphology, spatial structure, directional asymmetries, time-dependent geometry becomes the primary diagnostic. The paper's findings push the investigation into that regime, where interpretation depends not just on brightness, but on the arrangement of light in space, and how that arrangement evolves night after night. And in that regime, certainty becomes harder to claim, because projection effects, viewing geometry, and instrumental resolution all conspire to blur the line between what the object is doing and what our angle of observation makes it appear to do. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. To understand why jets might have been hidden until now, you have to understand how fragile faint structures are in astronomical imaging. 3 Atlas is a small distant object moving rapidly relative to background stars. Its coma is faint, barely distinguishable from the sky background in single exposures, and any jets embedded within that coma are fainter still. Standard image processing pipelines are designed to optimize signal-to-noise for point sources or symmetric extended objects, not for directional features that might occupy only a narrow angular wedge of the total brightness distribution. Background subtraction, flat fielding, and cosmic ray removal can all inadvertently suppress or distort asymmetric structures if those structures are not explicitly preserved by the reduction strategy. When the object is moving, aligning images across nights requires careful tracking of its ephemeris, and small errors in alignment can smear jets into noise or blend them with the diffuse coma in ways that erase their directionality. The paper's approach becomes a character in the story. The authors implemented custom image alignment strategies that track the predicted nucleus position with sub-pixel precision across epochs. They performed coma subtraction, modeling the symmetric component of the brightness distribution and removing it to reveal asymmetries, using radial profile fits that account for the point spread function of the telescope and the contributions from unresolved background sources. They applied time binning that preserves faint anisotropies, stacking only those images taken when the viewing geometry was similar, so that jets pointing in consistent directions across short timescales could add coherently while noise averaged down. And they used directional filtering techniques, searching explicitly for linear or arc-like features, extending from the nucleus at various position angles, to enhance structures that would otherwise remain buried beneath the symmetric glow. These are not new telescope capabilities. They are new analysis choices, decisions about how to interrogate the data, and those choices reveal structures that simpler pipelines would miss. But revealing structure through custom processing brings an obligation. The team must prove they are not manufacturing artifacts. Over-aggressive coma subtraction can create false jets by removing too much symmetric signal and leaving residuals that look directional. Directional filters, if poorly calibrated, can enhance noise patterns that mimic jets. Alignment errors can produce streaks oriented along the direction of object motion that have nothing to do with physical outflow. So the paper includes tests. The authors apply the same pipeline to synthetic data, simulated images of a symmetric coma with no jets, and confirm that the processing does not introduce false directional features. They compare results from different nights processed independently, checking whether jets appear at consistent position angles when viewing geometry is similar. They vary the parameters of the coma model and the strength of the directional filter, testing whether the detected jets persist or vanish as tuning knobs are adjusted. The jets persist. They reproduce across independent reductions. They survive the audit. And that survival shifts the burden of proof. The features are real enough to demand physical explanation, even if their interpretation remains ambiguous. What does it mean for jets to not sit still? In cometary science, jet motion can be quantified through several measurable properties. Position angle, the direction on the sky, measured in degrees east of north, at which a jet extends from the nucleus, can change from night to night. If a nucleus is rotating and a jet originates from a fixed vent, the position angle should vary periodically with the rotation period, sweeping through a predictable range and returning to the same angle after each complete rotation. But the jets reported in the paper show position angle changes that don't cleanly match a single period. They drift, sometimes smoothly, sometimes in abrupt shifts, as if the source region is moving across the surface, or as if multiple vents are activating and deactivating in a sequence that doesn't repeat cleanly. Curvature, the bending of a jet as it extends from the nucleus, can also carry information. Straight jets suggest ballistic dust grains following nearly radial trajectories. Curved jets imply acceleration after launch, possibly from radiation pressure, solar wind drag, or forces acting on charged grains. The paper's jets show curvature, and that curvature changes slightly between epochs, suggesting the outflow isn't simply following a static trajectory, but is being shaped by time-variable forces or changing launch conditions. Brightness asymmetries, differences in how much light is concentrated on one side of the nucleus versus the other, can swap sides over consecutive nights. If a jet is active on the sunward hemisphere one night and on the anti-sunward hemisphere the next, that swap could indicate rotation bringing different active regions into view, or it could indicate a change in which vents are producing dust. The paper reports such swaps, but the timing doesn't align neatly with an assumed rotation period derived from earlier photometric variability. And there are moments when a secondary jet appears, a fainter, narrower feature, offset from the primary jet by tens of degrees in position angle, only to fade or merge with the primary in subsequent observations. These are not qualitative impressions. They are measured quantities, angles, lengths, brightness, ratios, and rates of change. And those quantities, when plotted against time and corrected for the changing geometry of Earth's viewpoint, leave a residual pattern that resists simple explanation. This is where projection becomes both a tool and a trap. Earth's viewing angle changes continuously as both Earth and 3 Atlas move along their respective orbits. The Sun object Earth phase angle evolves, altering which parts of the nucleus are illuminated and which are shadowed from our perspective. A jet that appears to shift in position angle on the sky could be entirely fixed in the object's reference frame, with the apparent motion caused purely by our changing vantage point. Correcting for this requires modeling, assuming a rotation axis, a spin period, and a vent location, then projecting the expected jet appearance onto the sky for each observing epoch, and comparing that projection to the measured position angle. The paper attempts this correction. The authors test multiple combinations of rotation parameters, searching for a model that minimizes the residuals between predicted and observed jet angles. And here's the provocation. No single model fits cleanly. Some epochs match well. Others show systematic offsets. The residuals suggest that either the rotation is more complex than a simple spin around a fixed axis, or the jet source region is not stationary, or the outflow is being redirected after it leaves the surface. Complex rotation, specifically non-principal axis rotation, often called tumbling, offers a grounded explanation that preserves mystery without invoking exotic physics. Most small bodies do not rotate like spinning tops. They tumble, rotating around an axis that itself precesses through space, tracing out cones and wobbles on timescales that can be comparable to or longer than the primary spin period. In that regime, the orientation of active regions relative to the Sun and to Earth changes in complicated ways. A vent located at a specific latitude and longitude on the nucleus will not repeat its illumination conditions and viewing geometry on a simple clock. Jets can appear to drift, to skip expected appearances, or to show up at unexpected angles, not because the vent moved, but because the body's orientation shifted in a way that altered how we see the outflow. Observers would see exactly what the paper reports: drifting jet angles, changing spacing between recurrences, occasional missing jets when the geometry and illumination conspire to hide the active region or point its outflow away from Earth's line of sight. But tumbling alone may not be sufficient. The drift described in the paper, smooth in some intervals, punctuated in others, doesn't match the behavior of any single tumbling model the authors test. That mismatch suggests either that the rotation state is even more complex, involving multiple modes or a time variable spin due to torques from outgassing, or that the active region itself is evolving. Cometary nuclei are not static. Solar heating can propagate into the subsurface, reaching new volatile-rich layers and triggering activity in regions that were previously dormant. Surface mantles, thin crusts of non-volatile dust, can fracture under thermal stress, exposing fresh ice and shifting the location of active venting. If such processes are occurring on 3A Atlas, the jets we observe might be sampling a changing surface, not a fixed one, and the motion we measure could be real motion of the vent location across the nucleus over the span of days or weeks. There's also the possibility that the jets themselves, once launched, are not purely ballistic. Even weak outflows can be influenced by forces other than gravity and radiation pressure. Fine dust grains and gas molecules can carry electric charge, either from photoionization by solar ultraviolet light or from interactions with the solar wind. Charged particles, moving through the interplanetary magnetic field experience Lorentz forces, small accelerations perpendicular to their velocity and the field direction that can bend trajectories in subtle ways. The solar wind itself, a supersonic plasma flowing outward from the sun, can drag on dust and gas, creating asymmetries and directional biases that don't match the simple radial outflow expected from a rotating, outgassing nucleus. If the jets on 3 Atlas are faint and composed of small grains or significant gas content, these environmental forces could sculpt the outflow after launch, bending jets, shearing them into arcs, or shifting their apparent direction depending on the local conditions of the solar wind and magnetic field at the time of observation. Variable solar wind conditions could in principle alter jet morphology from night to night without any change in the source vent. A compression region in the solar wind, where faster plasma catches up with slower material ahead, creating a localized increase in density and magnetic field strength, could enhance bending or brightening of a jet if the object passes through it. A shift in the interplanetary magnetic field orientation could change how charged grains are accelerated or deflected, producing apparent rotations or offsets in the jet direction. This is speculative, but it's grounded in known physics. The solar wind is not uniform. It varies on timescales of hours to days, and those variations are measurable by spacecraft monitoring the heliosphere, correlating the observed jet changes with solar wind data, checking whether shifts in position angle align with changes in wind speed, density, or magnetic field direction, could test whether environmental sculpting contributes to the restless behavior. The paper does not yet perform that correlation, but it identifies the need for it as a future avenue. Now a different tension emerges, one rooted in timing rather than morphology. In the standard picture of cometary activity, brightness and jet visibility track together. As an object approaches the sun, solar heating increases, volatile sublimation intensifies, dust production rises, and jets become more prominent. As it recedes, activity wanes, brightness drops, and jets fade or disappear. That sequence creates an expectation. Jets should be strongest when the object is brightest, and morphological complexity, splitting, drifting, multiple active regions, should correlate with peak activity. But the paper's timeline doesn't follow that script cleanly. Some of the most pronounced jet directionality changes occur during epochs when the overall brightness is relatively stable, or even declining slightly. Jets appear at times when the photometric curve suggests activity is plateauing, not accelerating. And some of the clearest detections come from stacked images taken well after perihelion, when thermal models would predict that sublimation-driven outgassing should be weakening as the object moves outward and cools. This inversion, or decoupling, between global brightness and localized jet behavior hints at processes that operate on different timescales or respond to different drivers. Thermal inertia can delay peak activity. Heat deposited near perihelion takes time to conduct into the subsurface, and maximum volatile release may occur days or weeks after maximum solar heating. Crustal sealing can abruptly shut down one active region while exposing another. If a vent becomes mantled by dust that blocks further sublimation, activity shifts to a new location where ice remains accessible, and the photometric signature of that shift might be subtle even as the jet morphology changes dramatically. Fragmentation of surface layers, cracking, flaking, or collapse of overhangs can expose fresh volatiles in localized patches, triggering brief bursts of activity that produce jets without significantly altering the integrated brightness. Each of these mechanisms is physically plausible. Each has been observed or inferred in solar system comets. But distinguishing between them requires matching not just the presence of jets, but their timing, their brightness evolution, and their directional changes to the object's orbital position, rotation state, and thermal history. The paper does not resolve this timing puzzle. It documents the mismatch and acknowledges the interpretive challenge. Any successful explanation must account for both the morphology, the drifting, splitting, reappearing jets, and the photometry, the brightness curve that doesn't show the sharp activity spikes one might expect if jets were responding to sudden thermal events. That dual constraint narrows the solution space but doesn't yet point to a single answer. The investigation sits at a decision point, a branching of possibilities that the data in hand cannot yet collapse into certainty. Three broad reconstruction families emerge, each offering a way to explain jets that don't sit still, each struggling with some aspect of the observations. The first is fixed vents combined with complex rotation. The source regions are stationary on the nucleus, but the spin state is non-principal axis tumbling or a superposition of multiple rotation modes, producing a time-variable orientation that makes jets appear to drift. This explains the smooth, quasi-periodic changes in position angle and can account for missing appearances when geometry hides the vent. But it struggles to explain abrupt shifts or the appearance of secondary jets that don't fit the same periodicity. The second is evolving vents with changing illumination and thermal propagation. Active regions migrate across the surface as subsurface heat diffuses, mantles fracture, and new volatile deposits are exposed. This explains why jet behavior decouples from global brightness and why position angles can shift in ways that don't repeat cleanly. But it requires rapid surface evolution on timescales of days, which is plausible but difficult to confirm without resolved imaging of the nucleus. The third is weak outflow sculpted by environmental forces. The jets are launched from relatively stable vents, but solar wind drag, magnetic field interactions, or radiation pressure on small grains bend and redirect the flow after launch, producing apparent motion that reflects changing space weather rather than changing source geometry. This explains night-to-night variability and can account for curvature and asymmetries. But it predicts correlations with solar wind conditions that haven't yet been tested, and it requires the jets to be faint enough that environmental forces dominate over inertial ballistic motion. These families are not mutually exclusive. Real cometary activity often involves all three processes operating simultaneously. Rotation determines which vents are illuminated. Thermal evolution shifts where activity occurs, and environmental forces shape the outflow after launch. The challenge is determining which process dominates the signal, which effects are secondary, and how to weight them when building a model that predicts the observed jet behavior. The degeneracy is real. Different combinations of rotation parameters, vent locations, and environmental conditions can produce similar skyplane morphologies, especially when time sampling is sparse and spatial resolution is limited. Breaking that degeneracy requires better observational constraints, higher cadence monitoring to capture the full-time evolution, multi-filter photometry to distinguish dust-dominated jets from gas-rich outflows, and coordinated campaigns that track the object across a wide range of viewing geometries and heliocentric distances. Looking forward, the window for such observations is narrowing. 3I, Atlas continues outbound on its hyperbolic trajectory, dimming as distance increases and solar heating weakens. Jets, already faint, will fade further, and the morphological features that the paper worked so hard to extract will slip below the detection threshold of even large ground-based telescopes within weeks to months. Future observations will require space-based platforms, or the next generation of extremely large telescopes with adaptive optics, capable of resolving faint structures at high angular resolution. The Vera C. Rubin Observatory, when operational, will detect future interstellar visitors earlier and track them more frequently, providing the dense time sampling needed to distinguish rotation-driven jet behavior from thermal evolution or environmental effects. The James Webb Space Telescope's infrared sensitivity might reveal thermal signatures of active regions on the nucleus, offering a complementary view of where jets originate even when the dust outflow is too faint to trace invisible light. But for 3E, Atlas specifically, the data collected during its brief passage through the inner solar system may represent the only detailed morphological study we will ever have. The jets that drift, split, and refuse to anchor themselves to a simple pattern are, in that sense, a transient puzzle, visible for a moment, then gone, leaving behind measurements and questions. What the paper delivers is not a conclusion, but a sharpened set of questions. It establishes that jets exist, that they exhibit time-variable morphology, and that the variability resists straightforward interpretation through rotation alone. It demonstrates that hidden structures can emerge from careful processing of data that standard pipelines would discard as noise. It provides a quantitative framework, position angles, brightness ratios, curvature measurements that future models can attempt to match. And it acknowledges, with disciplined honesty, that the current data do not yet distinguish cleanly between competing physical explanations. The jets are real. The motion is real. But what that motion means, whether it's rotation revealing fixed vents at changing angles, thermal evolution shifting active regions across the surface, or environmental forces sculpting faint outflows in response to the space around them, remains an open question. In the end, the restless signature of 3I Atlas's jets is a reminder that interstellar visitors test our models at their edges. The rotation states, thermal properties, and structural integrity of objects formed around other stars may differ from the solar system comets and asteroids we've studied for centuries. Their response to solar heating, the timescales on which their surfaces evolve, and the ways their outflows interact with the heliosphere are all unknowns constrained only by the few visitors we've managed to observe. Every measurement, every drifting jet, every brightness anomaly, every morphological quirk, adds a data point to a sample size that remains vanishingly small. We cannot yet say what is typical and what is exceptional. We cannot yet build a robust taxonomy of interstellar object behavior. We are still in the phase of cataloging surprises, of discovering that the patterns we expected do not hold, and of learning that the questions we thought we could answer with existing tools require new approaches, new instruments, and a deeper patience with uncertainty. The jets on 3A, Atlas appear, drift and refuse to sit still long enough to be read clearly. They are a signature written in faint scattered light, distorted by distance and geometry, shaped by processes we infer but cannot see directly. And the most honest result of the paper is not a solved mystery, but a recognition that the mystery has structure, to stable structure, with predictions and observables and paths forward. The investigation continues not because the answer is obvious, but because the question has been clarified into something that can be pursued with better data, more sophisticated models, and the discipline to wait for evidence rather than forcing conclusions. The object will fade. The jets will disappear. But the questions they raised will remain, waiting for the next visitor, the next dataset, and the next patient effort to translate light into understanding.